Now, any questions concerning what I did this morning? Everything is almost clear. So we are working on this tricky issue of the namespace and global variables, global and local variables, and where they are defined and how can be used, and pass it through function to the global namespace or from the global namespace to local namespace of function, shadowing, and all issues connected to this. So we saw this morning that we, for instance, have this no good function that will not work. We define a counter equal to 1, so variable 1 defined within the function, no good. And then we'll print the value of this variable with this print message. Then this function defines a nested function inside, which is called nestfunc. And the nested func will redefine the counter, the variable counter, with this instruction here, counter equal to counter plus 1, and then pretend to print out the value of the of the variable counter. So the function nestfunc works in this way. Then no good function, the external no good function, will call, after having defined the function, will call it nested function. And the result is an error at runtime. As I explained to you this morning, the problem is that nested function shadow the value, shadow the variable counter with this instruction here. When the interpreter see an instruction like this one, what the interpreter will do is to shadow the variable, whatever it is, in this case is counter, with a new variable counter. But by doing this, it lose the value of the variable counter itself, which is not defined at this level, and try to upgrade counter by using counter itself. And so we get an error. Local variable counter reference before assignment. As the point is just that. This counter written here has nothing to do with the counter written here. It has been shadowed. So there is no possibility to upgrade in any way the counter value here by using this instruction, because the counter written on the right-hand side of this equation is not known. Then we define another function which I call isGood. It works, but do different things, because apparently do the right things, but in reality this nest function here will define a new counter value, which is stored in the variable counter2, which is not the same as counter. So this is another counter. It's not the same counter that you want. But when we run, we got these results. Now there is a way to work out to this issue of the local variable, and the way out is to use a statement, a declaration, inside the your nested function, which is the statement that starts with the keyword global counter. And you see that I use the statement global counter here in two places. I use the global counter declaration inside the function is good, in the namespace of the function is good, and also in the namespace of the function nest function. Now you'll see it makes around the cell. So I define the function is good in this way. Before doing that, I deleted the possible counter variable from the global environment. So if counter is in global, then delete the counter variable just to be sure that it's not present. Then I run is good, and I have the result, which is what we would like to have. So I have this counter which is defined at the level of the namespace of the function is good. And then there is this print here, counter, and the value is counter. So counter 1, first value of the variable counter is 1. Then the function is good, call nest func. And in nest func, you have this counter, which is upgraded, counter equal counter plus 1. And then print the value of counter, which is 2. So counter 2 come from this instruction here inside nest function. And then counter is upgraded again. Now the value it has is 2, plus 1 becomes 3, and then you have print counter 3. So what we did here is to use this global. This global declaration will save everything, but before going to explain exactly what global does, I can try to do something else. For instance, I can comment this statement here. I leave global counter operating in this nested function here. I will run the cell, and I'll try to work. I got an error. Name counter is not defined. If the same way I leave this counter, global counter active here at the namespace of the function is good, but I comment the line here, so this is not executed. I run this cell, I run is good, I got the same error. Local variable counter is not is referenced before assignment. So what? This is a little bit complicated, but anyway. When you use a statement which is global, followed by the name of a variable, the interpreter will create a binding of the local variable defined inside any function to the namespace at the global level, so to the namespace of the main module. So if I write global counter here, I define a binding of counter, the variable counter, at the main in the namespace of the main level of the main program. And the same is done here. In the namespace of the isGood function, there is also a binding of counter with a variable which is created in the namespace of the module. That's maybe a little bit complicated. Then I start with the other, another example here. This is a little bit simpler, then we'll be back on this one. Here, this one is a little bit complicated. But I will start here with another cell, which is a little more simple. Delete just the value of the counter variable from the main space. Then I define the variable counter equal to 0 in the namespace of the module. Then I define a function func. In this function, I will use this counter with global. So counter will be a global variable, and then I upgrade the counter variable, and I print the value. This is the work done by this func function. Then I call the function func, and the result is 1. So it works. Counter equal to 0. Then I call the function. The function will take counter and will sum it to the previous value, which was 0. So now counter is equal to 1, and the function provides the good result. Again, if you comment this line and try to see what happened, you get an error. Local variable counter reference before assignment. So it's happening exactly what we saw this morning. So in this case, there is a shadowing of this variable. So for the interpreter, the counter written here in this function is no longer the counter defined in the namespace of the module. And so it's not able to make this sum because counter on the right-hand side is no longer defined. But if I say that this counter is a global variable, it works because I'm creating in this way a binding of this variable counter with the counter variable which I defined in the namespace at the global level. So there is no longer shadowing, and the func function know how to calculate this sum because counter has at the beginning the value of 0 that arrived here. There is no longer shadowing. I create a binding between this local variable here with the global variable in the namespace, and so the result is correct. Take into account the global statement always create a binding between a variable and the variable in the main namespace. So in the namespace at the global level, in the namespace of the module. That's important. Here, I have a nested function. Imagine that I have written this function here without using the global counter in the namespace of the isGood function. What happened? You see, we get an error. Why? So the first print here is executed. When we call the function isGood, the first thing happen is the isGood function will assign a value counter equal to 1, which is not global. This is a local variable because global counter has been deactivated by using this comment here. Then print counter, so I got this message. Then I use the nested, then I define the nest function and I call the nest function. So the function isGood is calling the nest function. And what happened? In the nested function, there is indeed a global declaration, but this global counter will create a binding between this local counter variable, not with the variable which is defined in the namespace of the function isGood, but with a global variable outside the function isGood, so in the namespace of the main module. But in the namespace of the main module, there is it's not defined any counter variable. So it creates a binding to a value which is not existent. It is not already existent. So I cannot compute the following line here because I don't have the value counter. So counter is global now, but there is no any counter variable defined in the namespace at the global level. And so the function return the name counter is not defined. That's all. You have an error. The same way, if I put here counter and I do not put here global counter in the nested function, you get an error the same because the variable counter is referenced before assignment. Why? Because the global counter here defines a binding between this counter variable here and a variable in the namespace of the main module. But then, and so the isGood function will print, as before, the value of the variable here, which is now the global variable. Then call nest function. Nest function has not a local, a global counter declaration inside. So the counter here is not defined because it cannot work, because now counter is a local variable which is equal to the same local variable plus 1, but at the local level this variable counter has not any value, and so you have this error message. When you put global counter in both the definition of the function, things works. Why? The first global counter declaration in the namespace of the function is good, will make this counter equal to one variable as a global variable. So it will create a binding in the namespace, the main namespace, with a counter variable in the main namespace that will assume the value 1. The nested function do the same, create a binding between the local variable counter defined in the namespace of the nested function with the variable in the main namespace that now exists. Now exists because this binding has been created, because the binding was created by the function isGood. So isGood create a variable counter in the namespace due to the fact that we have a global counter, and the nested function bind the value counter here to the counter value in the namespace, the global namespace, and so it is defined. And it is defined by the value equal to 1, which is written here. And so return a number which is correct counter, which is binded to the main namespace. And so I can compute this structure, print the results, and then after the nested function is executed, the counter is again increased and printed. And so I got this correct result. If you now want to print the value counter outside the function isGood, I got 3. So the variable counter exists in the namespace of the main module, even if I created it inside the function isGood. So when the function isGood finished, every local variable that may be created inside the function is deleted, but not the global variable that was defined, and the global variable is now counter. A little bit complicated, I think. It's not that easy to understand this point, but it's worth the same. Now, this function isGood work correctly only because we create a global counter a counter variable in the main namespace, and the same is doing the function nestFun, which create the same binding with the same variable outside the function isGood. So in the global namespace. Is more or less clear? I know it takes some time to understand these things properly, but you have to do that. You have to understand. Otherwise, you will work empirically. If you don't study these things, you don't think about that, then you work by trial and error. You say, okay, I want to print my counter, I want to increment my counter from 1 to 3. And you see that, okay, you have to declare some global counter inside the nested function. And you do that, and you see, doesn't work. I have to insert a global counter even in the function isGood. But why I have to write twice global counter here and global counter here? Doesn't one global counter declaration enough? Is not enough? Why one single global counter declaration is not enough? I have to specify it twice. And I have to specify it twice because I want to create a variable in the main namespace to which bind the counter variable here and the counter variable that I use here in the nested function. So they are both binded to a variable in the main namespace. If I comment out, so say don't use any of these two global counter, then the things doesn't work, because this counter in the nest function will be binded to something in the main namespace which is not defined. Of course, I could do that. For instance, I can define here counter equal, for instance, 2. See what happens. Global counter here is not working because I put a comment here. I define a counter 1, and I have this global counter written here that will bind this variable counter to the counter defined at the level of the main namespace. What happened is that perfectly reasonable. Is good. Counter equal to 1. That's a local variable, it's shadowing the value that I have at the global level. So even if at the global level I write counter equal 2, here the message is counter equal counter 1, because the value that of the counter in the is good, the local value of counter in the is good function is 1. Then there is the nested function, but the nested function created the binding global counter with the variable outside the isGood function, so in the main namespace. And we'll use this to upgrade the counter. Counter equal 2 plus 1, so the value of counter is 3, and then it's printed 3, counter 3. Then the function finished, the nested function finished, and isGood simply upgrades the counter, which is its local function. It was 1 local variable, it was 1. So counter equal 1 plus 1 equal 2, and print counter 2. That's what's happening. So I ask again, is it clear?
Previously, we made an example where we were changing the name of the counter. So
Yeah.
we were not using counter,
Yeah.
but counter 1, counter 2. In this case, we could not do that, right? In this last example that we saw.
We in the last example we can, but we will have another variable which is counter 2.
Okay.
It says another variable. With this function is good written this way with 2 counter variables. It work, but it's not doing what we want. Generally, when we want to count a number or ways a function is called, for instance, you want a single variable to be upgraded every time. But we are not a single variable. We start with a variable which is counter equal to 1, then we define a new variable which is counter 2. That at the end of the function is also lost. For instance, if I run this function here, this way, no, it is not this function here. Where's the function? Counter 2, okay. Okay. And now I want to print the value of the counter 2, for instance. Print counter 2. I have to put parentheses. Does not exist, because it was a local variables defined in nested function, and when the function finished, that's deleted. The same is true for counter. Not existent, because counter is a local variable inside isGood. So when the function finished, there is no longer the variable. In this case, it's different, because this counter is a global becomes a global variable, we can declare it as it is, and so it will be preserved at the end. So I can run print counter from the main namespace, and I have the last value I computed. So this is preserved. It can be used by other functions for doing some other elaboration. So there are 2 different way to work, and this is generally the way we want to work.
Thanks.
Okay, now can delete this one. Too many print counters. Okay. We already encountered this one. Okay. Now we have another possibility. We have this very, very similar example, but we use another statement, another keyword, which is not global, but it is non-local. And very useful in case that you have to work with nested function. I define a function which define in terms a variable, which is counter equal to 1. Then inside function, inside func, I'll define a nested function, nest func, that will use this counter equal counter plus 1. Then I say non-local counter. So before I write this, I execute this instruction here, I write this instruction. This is not an instruction, this is a declaration. Non-local counter. This non-local counter will create a binding not with a variable in the namespace, the main namespace, but with a variable that must be present, and I will say something more after, with a variable that must be present in the namespace of the function that contains this nested function, that define this nested function. So non-local counter will not create a binding with a global variable counter, but will create a binding with a variable counter which is defined in the namespace of the function func. Now we run the cell to see what happened. Okay. So the first thing the interpreter does is to define this variable counter in this namespace. Then read the definition of this function, then print before the call to nested function counter, so we'll print the value of the counter variable here is 1, is this value here. Then call the nested function. The nesting function binds its counter to the counter value here, so it is able to compute this sum because it knows the value of counter, the variable here, so there is no shadowing. This variable counter here in this namespace is not shadowed by the counter defined here because there is this non-local counter. And after the function finished, after the call to the nesting function, print counter. So after the call to the nesting function, the value is 2. So inside the function, the variable counter is being defined and then it's been upgraded by a nested function. What is the difference between this definition using non-local and the previous one? The practical difference is that if we now try to print the counter variable from the namespace at the global level, I got an error. Counter is not defined differently as before, because counter is not a variable in the global namespace. So this non-local will create a binding with the variable in the namespace of the function defining the nested function. But differently, also, there are another difference. Differently from before, when I use global, I will create a binding with a global variable which does not necessarily exist. Global can be defined before in the namespace at the global level or not. If I define a variable here in a function and I define a binding with a global level, the variable will be created in the global level. So it can exist before or it cannot, does not make any difference. Non-local now work a little bit differently. So the local The non-local variable counter in this case must be binded to a variable that already exists in the namespace of this function. So if I make, for instance, I put a comment here, so the variable is not defined, and I try to run it. So before I call the function name in the function, so at the definition, time of the definition of the function, I got an error. No binding for non-local counter found. So I cannot find any variable counter to which I can bind this counter defined inside this function here, inside the nested function. So the variable must be already present in the namespace of the function defining the nested function, and everything will work. Okay. Now the function is not, counter is in global as well, so the variable counter is not present in globals. Okay, now I give you 5 minutes, maybe less, 3 minutes maybe, because it's simple, to understand what this factorial function do. So this is a function that calculates the factorial of a number by using recursion and by using this non-local construct. So I can maybe increase a little bit. So you have this factorial function. Try to understand what I'm doing here. So I try to explain. we have to compute the factorial of a number. I define a function factorial, which takes as argument the number n of which we have to compute the factorial. Then I start to define the factorial, the variable that will store the final result, and I initialize it to the value 1. Then I define a nested function inside factorial, and I call it recfunc, and rec stands for recursive, because I'm going to use recursively this function here. Then I create a non-local binding of this fact variable here with the fact defined here, and also a non-local binding of this and with the argument of the factorial function. So fact will assume the value of the variable fact here, and n will assume the value of the argument n here. And I'm going to do that because I use this non-local because I'm going to change both the fact variable, so I have to reassign, to upgrade the variable fact, and also the variable n. So in order to work properly, I have to create binding with some variable which already must exist in our namespace of the factorial function. So what happened? At the beginning, fact is equal to 1, n is equal to, let's say, 3, if you want to compute the factorial of the number 3. Then fact will be equal to 1 times 3, and n will be downgraded to the value 2, n equal to n minus 1, so it will become 2. Then there is a check. If n equal to 1, then return. Return means exit from this function recfunc, from this nested function recfunc, and the control of the workflow return to the function factorial. Otherwise, call again recfunc. So if n is not equal to 1, the function call itself. But now factor has been upgraded, okay, with respect to the previous value 1, and also with respect to n. So this factorial function, this recfunc function, call itself a new argument now, with new variable inside. So you have a new fact that will be multiplied by n, but now n is no longer the n that we have written here as argument of the function, because it's been decreased by 1 unit. So if n before at the beginning was equal to 3, in the second cycle that the recfunc call itself, it will be equal to 2. So we will multiply fact by 2 and not by 3. Then n will be decreased again. But now if n is equal to 2, 2 minus 1 is 1, and then n is equal to 1 is true, is a Boolean expression which is evaluate to true. So if n equal to, if this is true, then return. So the function do not call itself again, just return the results. So what happened? Now, this is just a definition of the function. The function factorial define this function and then execute the recfunc. So we are at this level. This the recursive operation are done. And then when the recfunc return the control to, with this return the control to the factorial function, the next operation, the next instruction is just return fact. And so return fact will give us the factorial of the number. So I run the cell, and then I compute the factorial of 8 in this way. Questions? That may be tricky. Every time you have to use a recursive function, it's probable that you have to make use of non-local declaration like this one.
If we not write non-local, we get an error, right?
We can try.
Because
We can immediately try. I define, so no problem at the run level, at the definition level, but at the run level, I got errors. The local variable fact reference before assignment. Why? Why? Because fact is no longer binded to the value fact that I wrote here. And so this is a new variable. This is a local variable defined in recfun. This is local because it is not non-local. And then this fact written right hand side has no value. So the interpreter is not able to make this computation and return this local variable fact reference before assignment. The same is true if I write, for instance, fact. I can put here non-local fact, but I forgot to put also n, so I can run it and see what happened. I, of course, got an error. Local variable n reference before assignment. Why? Because now n is no longer binded to the value of the argument of the factorial function here. And so we have a problem here because you cannot compute this expression here or of this expression here because the function does not know the value of n. One can say, okay, I can define n outside in the global namespace and then, for instance, compute something. No, it doesn't work again. The same. You see now that it will not work because now this n is still a local variable. Okay, you say, all right, but I can write here global n to bind this variable n to the variable that I have outside. And it's work. It never stop. Why never stop? Okay, never stop. So I exhausted the What happened here? It happened this problem that I put n equal to 1, then I call the function factorial. Factorial create fact, okay. Fact is non-local in this nested function, recfun, that's okay. Then I define global n, so I bind this variable n to the n here. And I can compute this fact, no problem. Then I decrease n, and n becomes n minus 1, so it becomes 0. And 0 is not equal to 1, so the function does not exit. And then does not return, and then I have the call to the recursive function itself. So the function call itself gone. N is n minus 1, so it was 0 and becomes minus 1. And the next cycle could be minus 2 and minus 3 and minus 4. It will never reach the value 1. So this function will continue to call itself in an infinite cycle. If I put here 6, for instance, that should stop some point. Let's see what happened. Okay, I got a factorial, and I got a number here. At least I got a result. I have to check if the value is correct. Maybe it is. If I put 3, it's a correct. So, but you see the strange thing. Factorial 8 is 6. No, it's not correct. What's happening is that I leave this n here, but in fact I can eliminate this n here because now the n is no longer an argument of the function, Is this defined already at the global level? So, okay, this is ignored when I call the function just factorial is the number 6. If I want 4, okay, 24. What's the problem? Well, very, very unelegant way to work, because I defined a function to compute a factorial, but I have to define at the global level the value of the number of the factorial, the value of the number that for which I want to compute the factorial. It's a very strange function. So a function that should have an argument, but the argument is defined at the global level. Not very good. Never do that. So arrange things in order not a function will work with data that you can define, for instance, as an argument of the function. So you have n here, and you put your correct definition, non-local definition here in this way. So create a binding between this n and the argument of the function, and then make your computation. Okay. More or less clear? Not so simple. Not so simple. Because in this example we have recursion, which is not a simple concept. Well, the idea is not that difficult to understand recursion, a function that calls itself. The problem is always in making recursive function is always the implementation in a specific example. So one say, all right, I want to compute the factorial of a number using recursion. Well, but how I write the code? That's the problem. It's not understanding the fact that the function can call itself. And so we have another function here. I'll give you again a couple of minutes. We can compute the square root of a number by using the method, the Newton method, the Newton algorithms. And so the formula that we use is this one. The square root of a number n is the limit for m equal to infinite of xm, and xm is computed in this way, recursively. You have a starting guess for the square root of the number. You can call it 0. And then you write this formula, 1/2 of x0 plus n divided by x0. And you use this number, you assign this number to the value x0 plus 1, so to the number x plus 1, which is I plus 1, which is just x1. Then take this x1, put inside your expression here, so you have x1 plus n divided by x1, take half of the value and assign to x2. And go on until you stop based on some criteria that we will see. So this is the algorithm that you have to implement. I implemented, and you have to study the implementation to compute the square root of a number recursively. This is a good example for using recursion, because you see that I have a number x I plus 1 that depend on what you already obtained at the preceding steps with index I. So a good example, a good candidate for working with recursion. So here's the function, and try to understand what it does. By the way, in NumPy, we have numpy.sqrt taking a number n as a computer. It computes very fast the square root of any number. But we don't want to use NumPy. We want to use Python and to compute the square root with Python.
Sorry, so the initial guess is the number I want to
Compute the square
use.
root.
Okay.
That's a possibility. We can also make an initial guess which is different from the number, but that's a reasonable assumption. So, define the square root function. Our obvious argument as a mandatory argument is just the number of which we want to compute the square root, this number n. And I define also here an optional value which I put to the value 1e minus 15. This means 10 to the minus 15, to a very, very small number. And we will see why. I define it. This is a keyword argument, which is a default, which is provided, which is this number. We can also change the default when we call the square root function. Then I put guess equal to n, this variable guess equal to n. And also I make a little check here. If guess is equal to 0, then put guess equal to 1. Now, why I put these things? I can put all other instructions too. But the fact that one could, for instance, try to compute the square root of the number 0, just for fun, just to check the algorithm or something like that. And what happened in this case, and that this guess is equal to n, and n is equal to 0, then the formula, you will have an n divided, 0 divided by 0. In any case, you will get something which is not defined at the level of the interpreter, and so your square root function will provide you an error, and will end with an error. So in order to avoid the error, I check if guess is equal to 0, and in case, I will put guess equal to 1. That's all. And this is nothing important, just to prevent a bad use of the function, providing you an error and not a number. Then I start with this guess equal to n, and then I define inside the square root this other function. So this is a nested function, which is recursive because in some point of the body of the function call itself. So square rect will be called inside the function square rect. So it is a recursive function, and this is the reason for which I call this function square rect. It has no argument. Then I have this variable guess that will be created every time. And so I define a non-local binding of this guess with a guess defined in the namespace of the square root function. So I have this declaration. Then I compute the next iteration, the next value of the iteration, which I call approx. Approx equal to 0.5, just exactly 1/2, plus times guess, this xie here, plus n divided by guess. So this is the point for which I have to assure that I don't have a guess equal to 0. I check it here. So I have approx equal to 1/2 guess plus n divided by guess. And then I see what is the difference between the approx value, the approximated value, and the initial guess, and the guess that I have at some point. Now, if this difference is greater than the threshold, this THR stands for threshold, that I define it, then I'm say that I'm not satisfied with the approximation. I didn't reach a convergence within the value 10 to the minus 15. And so I will put guess equal approx, so I will upgrade the variable guess to the value I computed here, to the new value that in this case plays the role of x over I plus 1. And then I call again the function recursively square rec. So again, I will calculate a new approximated value by using the new guess I computed at the preceding step. I will evaluate the difference between this number and the previous one and check if the difference is above or below the threshold I chose. In case this diff is lower than as a number which is lower than this threshold, then this condition is false. This is no longer executed because the condition is false, and the alternative expression will be returned, which is return. So the def square rec will finish, the function square rec will finish. So when I define square root, what happened is that the function first define an initial guess, check if it is 0 or not, define the function square rec, and then call square rec. The function start, and when it's finished, it will return, and the value and the control of the execution will pass again to the function square root that will execute return guess. And the guess here is the last value we computed for the approximation. We will get our results. And try this function. I will run it. I will run the cell, and I try with square root of 2, for instance, and we got the square root of 2. Of course, it worked for any number. 2, 3, 4, 5, 7, 3, 2. We can compute it, and we got this number. One say, all right, I'm not so. We don't need very, very high accuracy, so maybe that threshold could be a little bit larger value. So I can write here, for instance, square root of 2, and the threshold equal to, let's say, not 1, maybe 1e minus 3, for instance, so a large value. And we got a different, a slightly different value, probably because the threshold is a little bit high. Okay? Everything is clear?
One question. What is the ABS? Diff, equal, ABS?
ABS, absolute, yeah, I forgot to say. ABS is the absolute value. You see that this threshold is a positive number, and I want to compare this difference with this threshold, which is a positive number. And this approx could be smaller or larger than guess, depend by the type of calculation that you want to do. So generally, when you make comparison like this one, it's better that you use the absolute number of this difference to prevent to have a negative number. For instance, if approx was much less than guess, I will find a negative number. It could be very large in absolute sense. It could be, for instance, -1. -1 is much lower as a relative number than the threshold 1e minus 15, but its absolute value is very large. So I will find -1 is greater than the threshold. No, it is not greater than the threshold, and so this statement is false, and the function will end getting a wrong value for the result of the square root of 2. So I take the absolute value of the difference. So I want that these two numbers are very close one to another, not looking at the relative value, but I will look at the absolute value to compare with the threshold, which is a positive number. So ABS just that. Take the absolute value of a difference, or in this case of an expression, which will always be positive.
Okay. Yeah.
Okay, if that's a little bit clear, there's it's not a warning, but something that can complicate things when you work with arrays or lists. So I have this list here, which is initialized at the global level. So this variable A is a list defined in the global level the namespace of the main module. Then I define a function, and this function, the first thing it does is to redefine the A variable, this list, and you see there is no global, no local declaration, nothing of that type, just the value A equal to 6, 7, 8, print A within the function A, and so this function is defined this way. Then I will call the function, and then I print A outside the function. What happened is obvious. A within the function, A is defined this way. A as this is being redefined inside the function func. So this is a shadowing, the typical shadowing, because there is no global declaration. Then the function will print this message here. So it will print the variable A inside the function. And I get 6, 7, 8, which is exactly this value here. Then the function end, and then print the flow of the cell will print the A outside the function and will return to the value, the initial value. So we got this list here. And the value within the function was a local variable shadowing the global variable, and it has been deleted. Usual shadowing that we will see before for normal variable. But look at this other example. I define the variable as a list. I define this function that do not reassign all the array A, all the list A, but just one element. So A0 is equal to 7. Now, in this list above, the element having the value in the first position was this 1, and I have the value 1. Now I put A0 equal to 7. Okay, one could say, all right, but what's the matter? Now, this A is not binded to anything outside because there is not a global declaration. So A0 will be simply a variable, an element of a list, A0, and I will change it to 7. I will put it to 7. So I assign the value of a list in this way, the first element of the list, and then I will print it. And so what happened here is that A before, then I run the cell, and what happens is A before the function call 1, 2, 3, 4, 5, exactly this one. Okay. Then I call the function func, and what happened is this thing here. So the value of the first position has been changed to 7. We have to think about that. It's been changed to 7. All right, okay, it's obvious because I put here A0 equal to 7, so I expect that the position here will be changed. That's strange. That's strange. Even neglecting this other call here, this other print here, these things should be okay. This thing is not so bad. Now we have this. We know that this variable has been defined at the global level, but this should be shadowed inside the function func here because I am reassigned something concerning that variable. So this A inside the function should be a local variable, and I'm trying to change the value of an element of this list that should be local. But how does the function func know what is this list? So to be clear, I think that this is not clear at all. But for instance, delete A. So there is no A. Haha, it got an error. There is no variable A in the global namespace. So I cannot do this operation here because this is not an assigning of a local variable. You see that name A is not defined. If I write this way, and I run I got an error here, but oh yeah, I got an error because I put A here for this one. Now I got an error here. Print A before function call. Okay, it's I'm trying to see what's happened here. So right before the function is called, there is no value A, so I can comment this one. Okay. Okay. You see what I see, what I have. Now I have no errors. That's from A equal to 7, print the value of A. Nothing strange. This print is done at the level of the function func, so in the local namespace, and I got 7. But if I write here as 0, as before, I got an error. A is not defined. So wait a minute. Why if I write A, simple A, I can assign A to some value, 7, and I print it, and I get a result, which is exactly 7. But if I print A0 equal to 7, the interpreter understands that there should be somewhere an array, a list with some index. If there's a list, it has indexes, and I can assign value to the element of the list. I have no list here. Because it is not defined at the global level. So the interpreter is not able to retrieve any A0, any element of the list in position 0, because there is no the list. So it doesn't work. This is not working because A is no longer a single scalar variable, but it is a list. So I have to define the list at global level, and now it works. I start with this list 1, 2, 3, 4, 5, and then I change, within the function, I change the value of A, of the list A, by changing the element in the first position, so the element with index 0. And I print it, and I got 7, 2, 3, 4, 5, because the value 1 has been substituted by the value 7. But the strange thing is that if I print A after the call, you see that this A after the call is the same as the A that I have within the function. That's a big difference with respect to what we see in we saw before with scalar variable, with single variable. I try again here. A equal to 1 to 7, and I print what happened. You see, A is equal to 1. The function call it, so shadow the variable A, which is the new variable A, assign it to the number 7, print A inside the function, got 7. But then when the function finished and I print the value of the variable A, I return to the original value. So A after func call is 1. But if A is not a single variable, a single number, but it is a list, in this case, I can assign different element of the list, and I will have modified permanently the list by using a function that assesses the element of the list. Why it happens? Well, it's not easy to explain for me this why it's happened. Anyway, the fact is that A is just the label that point to some location in memory. And when we do an operation like this one, A0 equal to 7, we don't work on the label representing or pointing to the location of the memory. We modify the content of the memory. So this is done permanently. A0 equal to 7, I'm changing the content of the list A. I'm not simply changing the label which I assign to the list. List A is this one, and I don't change the label. I'm not shadowing the label with another label defined at a local level in the function func, but I'm changing the content of the memory. So when the function ends, the content on the function func ends, the content of the memory has been modified by the function func, and so the label is pointing at the same location in memory, but that location in memory contains value which has been modified in this way. So the first element of the list will be 7 and not 1 as before. So pay attention when you work with lists and you modify element of the list inside a function. This has a permanent effect on the original list. So you can modify element of a list in this way. It could be useful some occasion. You want to make modification to some list that contains information that the program can use later. And you cannot do that with scalar numbers, not list, just a single variable, because of this shadowing and global and non-local and declaration and so on. You cannot do that. But you can modify the element of a single list. So it can be useful, but it is considered a dangerous practice. Because when you write very complex program containing a lot of functions that can do a lot of other things, and you modify elements of a list in this way, very rapidly, if the program is complicated, you will lose of which function is changing what. And then if you get errors, bug after some times that you use the program, it will be very, very difficult to find the bug, for finding where the errors originates, because maybe there is some function among hundreds of functions that you wrote in your program that change in a way which is not controlled, change the value of some element in a list. So if you do that, you can do that, but pay attention, that can be dangerous, can be origin of mistakes and errors and bugs of your programs if the program grows very large. For instance, imagine the program here that yesterday I told you something about this project I am working on, and you see this program contains hundreds of functions and arrive to about 8,000 rows, so 8,000 instructions, very long, so a lot of function inside here. And if I start to change things, list in an uncontrolled way in some function defined inside the program, inside the module, it becomes a mess. The program will become unusable, and if errors originate, then it will be very difficult to find them. So this thing can be done. This operation can be done. If you do it, recall that when you did it, and if you do it is because you don't have any other possibility to work. So you consider all the possible alternatives to an operation like this one. If any one is good enough for you, then you can do it, but try to use, to think at least, try to think to other possibility to change arrays or lists without using this way, because it is considered a really bad practice. That's a bad practice, because a practice that will generate error very easily at later time. So this is a back practice, but also back practice is use globals. The global declaration can be used. It's legal, but it is considered a dangerous practice. So global declaration is something that allows a function to change the value of a variable which is defined at the global level. So you can do that, you can use global, but take care that it can be dangerous. Things that it can be dangerous. There are other ways of working, maybe in many occasions. So don't use globals as you can. If you can, at least don't use global to upgrade variables that are defined in the namespace level. Okay. This is another example. Okay. I say don't use global, but I use global sometimes. For instance, but very limited in some particular. For instance, I have here a function in my project to read the file, and file contains a lot of variables that are needed to the program to work. And so these are defined, these variables are read by this, defined in this function that read the file. So I constructed a function that go on the disk, will read the file, and then will define variables and do something according to the input that is present in the file. But then this variable that are read from the file must be used by other function of the program. So if I want to use this variable in other part, they should not be deleted when the read file function exits. Otherwise, this unuseful. They are unuseful. They are no longer defined. So I define a large number of global variables. These are all the variables that the program will need for its execution. So they are read in a function, but they are defined as global. But I use this global very seldomly. For instance, I use global here. Then I use global, and there's a block of global in another point. Okay, here, there is a function. It's called static. It's defined this global variable pcover. I know exactly what it is, so I will make attention not to change it improperly in some other part of the program. And there is another block of global defining this function main, which is exactly is essentially the main function of the program that will control everything and needs all these variables to be defined. And stop. I don't use global in any other place. So I have this in this read file, in the main, and in one single function among 100 functions that I build in my project. So if you can, never use or use in the proper ways the global declaration. Now, we see what happened when I address some elements of a list by using this argument to indicate the position of the element in the list A that modify permanently the list. But, for instance, in this other case, where also I use a list, it doesn't work. Okay. In this, the error is wanted. Now, in this other occasion, you see that I have A is a list. Now I have the function func that takes this list and multiply by 2. This is a concatenation of the list with itself. Because we are in Python, we are not in NumPy, so this is a list, and this should take the list and replicate it twice. But I got an error. So what happened here? This cell defined at the global level A, then define the function, and then print A before the function call, and this is this variable A, this list A, which has been printed, then call the function, and at this point it gets an error. Why? Because, and the error is variable A, local variable A is referenced before assignment. You see that here I have a shadowing. I'm not, even if A is a list here, I'm not addressing elements of the list. I'm addressing the whole list. And so I'm addressing the label of the list, not the content of the memory pointing at the list as it was doing here. I was doing here. Here I am addressing a position of the memory. Here I address the variable, a label, a pointer to something, which is not defined at this level because this is a local variable A, and I want to make A equal to A times 2, but the interpreter does not know what this A is. So, because of the shadowing. So if you address the full list, the label of the list, it works, everything works like A was a single variable. If you address elements of the list, then you have this permanent change. What I can do now is to put a declaration, global equal global A. And so what happened here, I define a binding here between the variable A, which is the list, with the list outside. So A is defined at the level of the func, the function func. Now, A before the function call is 1, 2, 3, 4, 5, exactly this list. Okay. Now, I call func, and func take the list, and multiply it by 2, and I have the concatenation of the list with itself. So I 1, 2, 3, 4, 5, and again 1, 2, 3, 4, 5, because I make A equal to A times 2. And then print it. So this print, the second print, A within the function is generated by this print instruction here. Then I print the list after the function call, and I get this list, exactly the same list as the list here. Why? Why? Because now there is this global A. So global A bind the value of A to the A at the global level, and so the list is permanently changed. So there is no shadowing. I had the function func modify the whole list, and this is the result. Okay. Let's see what I'm trying to do here. A equal to a list. Now I define this function factor, and I multiply the value of the list here. See what happened. Okay. For IA in range len A. Now, len A is a variable defined at the global level. So it is it is not shadowed by the function func. There is no an assignment at this point of the label A here. But I address here the elements of the list. So it can be done. I can do that. So the variable A is here, is the list, and so it is known at the level of this function func. And for the IA in range len A, so for all the value of IA that go to the position, through the position of the elements here in the list A, change the content of the list. So point to the memory of the computer and change the content of the list, element by element. So I1 equal to I1, the first I0, the first element of IA will be 0. I0 is equal to A0 times factor. Factor is an argument, the argument of our function here. Then go to the second and to the third. So go through all the possible IA in this list of integer. And then in this cell, print the value of A. So print this list. Print call the function func. Okay, this function func will do this operation of multiplication by the number 4. Factor is equal to 4. And then print A after the list has been, the element of the list has been multiplied by the factor 4. And the result is a permanent change of the list. You see that all the elements has been multiplied by the number 4, 4, 8, 12, 16, 20. And this is a permanent change. Why? Because I addressed the element of the list, not the whole list. Yes, the same with the NumPy. The NumPy arrays, the same results. So even if A is not a list, but it's the NumPy array, and I use this function factor to multiply the elements, I got the same results. But what if I make this operation? You know, NumPy has the broadcasting facility. So if I multiply a list or an array times a factor, all the elements of the array will be multiplied by the same factor. What happened is that I got an error. Why? So I define my array, I define my function factor, and I print A, so the original A, 1, 2, 3, 4, 5, that's correct. Then I call function func4, more or less as I did before. But I got an error. Local variable A reference before assignment. It doesn't work in this case. Why? Because I'm addressing not the elements of the list, as I did here, not the element of the array as I did here with IA. I addressing the full list, the label of the full list. So I'm shadowing the value of A here. I'm shadowing the list A, the array A. And so the interpreter is not able to compute this instruction because it doesn't know how to evaluate this A on the right-hand side of the equation, the assignment. A is referenced before assignment. So you see the difference. I address the list as a bool, I got an error. I address the element of the list, the element of the array, there is no error, and the function works. Of course, I can do this. I can say, all right, I want to work with a function like this one, but I want that this function will work. So what I can do is I can simply use a statement global A. So I will bind the A here inside with the A defined at the outer level. So there is no problem now. The interpreter knows how to compute this right-hand side, and so it will multiply by the factor, which is 4, and print results. So you see 1, 2, 3, 4, 5, and 4, 8, 12, 16, 20. So I modify permanently at the global level the A array by using this global statement here. So as I told you before, global statements are perfectly legal, but they are so-called deprecated. So generally people use them, they can use them, the program works, the program, the interpreter doesn't get angry if you use the global declaration, but they are source of errors. So if you can never use global declaration. Whereas the non-local declaration, used for nested function, is much more sure, much more safe, not sure, is much more safe because makes binding defined with very specific namespaces, not at the global level, but at the level of the function defining the nested function. So they are generally safely used, but not the global declaration is dangerous. If you see a program written by other cluttered with a lot of global declaration here and there in any function, there are global statement that the program is not well written. The programmers didn't follow any good practice, and very probably in the program will present later on sooner some bugs that happen because the global support errors, in fact. So this is the most tricky part on the Python programming, that you have to get accustomed with this problem, this variable, the namespace, where the variable exists, and so on. Other languages similarly issue. For instance, if you have the Fortran, if you use Fortran, Fortran has generally used subroutines. So you define the main programs that call subroutines, and each subroutines can call other subroutines. And every subroutines define its local namespace and communicates the variable values through the so-called common block. So you define a common block, which is a list of variable or array that are exchanged between the main program and subroutines, or between subroutines and other subroutines, by sharing this common block. Common block that you define by using a keyword which is called common, and you can also assign name to the common blocks, are inserted whenever needed in every subroutines in order to transfer a variable from one place to another. And in the case of the Python, we have this other method. So we have this global variable. So all the variables which are defined at the namespace, the main namespace, are transferred to the function unless they are shadowed. Or you have this non-local declaration that allows you to share value between the function and some nested function inside the function. Or you have just your local declaration, just local function, local variables. Questions? There are no questions because you don't understand anything, or there are no questions because everything is clear? Generally, the first case is the case.
I think it's clear, but I don't know if in practice I will be able to use everything properly at the
Well,
first try.
practically, what you have to do is start to work. So you have to start to write very little, very small, short scripts in Python. And so you don't start by writing something like this one, but very, very small scripts. And you'll try, and after you try, you will understand. So you see, oh, okay, now I understood why it's all that, why it works in the way, why it doesn't work. And then the point is understanding the fact that there exists this issue, and that you have this global and non-local, and then you can make some experiments. When you make some experiments after some time, a very short time, that doesn't require so many time, you will understand. You will learn how to use these things. But you have to practice. You have make experiment. You have to make the experiment by yourself. Otherwise, this is just words. You finish this lecture, and okay, it's a right difficult issue, and I will not be able to do something. But you have to don't give up, and try to make experiments. With the experiment, you will work. first times you will write, you will get a lot of errors. Almost every line of code you write, you will return you an errors. And at the beginning, you will not understand anything. But with some patience, then you will succeed. That's guaranteed. You will succeed for sure. Differently, if you start to work on Python without following any advice, any lecture, just by examples, you say, right, your boss give you a program, says, all right, look at this program and study what it does, try to use it, and then try to extend it in some way. So I would like to have another function that do these things. Then you have no any preparation on Python, and then you never studied nothing. You never learn nothing from somewhere else, and then you will try to learn by example, by looking at example. But example are not explicative. They're just particular situation that happen to works, but you don't know why they work. And then when you try to extend the program to do something else, it does not work because you don't know why. In some cases, this global statement, and in other cases, not use. You don't understand why you have to use two global statement inside a function, inside a nested function, in order to the function to work, and so on. But if you know that the issue exists and it has been discussed somewhere, you can go somewhere and relook at this notebook, for instance, and you will understand everything. So the message is that you have to try. If you don't work, if you don't try by yourself, that's things become very, very hard. Now, still have some minutes, so I will go on a little bit. I said if you can never use global statement because they are source of error. Okay, that's good, but maybe that we want function that create variables, that define variables, that modify variables, that will be passed to other function and will be passed to, for instance, some routines written at the level of the main namespace. So you want function to be able to produce variables which are stored some way and which are not deleted as soon as the function finished. Yeah, all this example that we saw are just toy examples. So it is not a problem if a value of the local variable defined in a function will be deleted after the function exits, because we don't do anything else here in this toy example. But a program is a collection of functions, and the function do something, and this something must be communicated to other functions. So you want that function modify variables, and these variables should be stored somewhere after the function exits. And information technology people tell you don't use global if you can. So what else? What's the alternative to the use of global declaration, the global declaration, if you don't have to use it, but you want the variable to be stored somewhere? So the best thing to do is use class. So I told you at the beginning of the course that classes are everywhere in Python and support so-called object-oriented programming. So you will use classes every time, even if you think you are not using class. As I told you, if you define a number and assign an integer number to a variable, you are already using classes because you are using the integer classes, and you are creating an instance of these integer classes to store a variable. If you write a equal to 1, you are using the class. You are using the integer class, and you are creating an instance of this class, and the name of the instance will be the variable a, and you will attribute to this variable a value which is equal 1. So you always use class. So now what we should do now is give a look under the hood of this class methods and see what really classes are. And you have to understand what classes are, and you have to learn how to use classes to create new classes and to store variables somewhere in your programs, variable that can be changed by function somewhere in your main module. So let's start for some minutes to see some definition at least. So I delete the kernel and clear the output of the notebook. All right. Now, here I start to define a class. Now imagine that you have a program that must use some variables, some constant that you don't want to change. It is not likely changeable during the use of the program. So for instance, and with the calculation I do every day, I use the Planck constant, I use the Boltzmann constant, the Avogadro constant, the gas constant maybe. They have definite value in some unit of measure. And probably I will call them H, K for Planck and the Avogadro and the Boltzmann. The Avogadro is simply Avo, and the gas constant is called R, could be called R. I can start a program, a module, by writing, okay, A equal to, K equal to, Avo equal to, R equal to, and assigning some numbers. H, K, Avo are just somewhat anonymous names. It's probably that during the course of my program, I will use H for other uses. I will assign H to some other variables that define completely different things, and I shadow in that way the value of the Planck constant. So if I use H at the main level of the program, so the main module, I define H equal to 6.62 and so on. And then I write a function that use H for something else to define H at the local level. But then also needed the Planck constant. Well, the Planck constant has been lost because in that function, the Planck constant has been shadowed by the new variable that I defined at the level of that function. So no good to give it some anonymous name to our fundamental constant. So one thing which is useful is defining a class, in this case, that will define, in this case, the value of this constant. So I use this keyword class. Then it is followed by a name, constant name that I can choose. I say constant class, constant underscore class. And then I put here parentheses without putting nothing here inside for the moment, at least. Then colon. And then I start to write something after this class here, indented in some way. And the first thing I define here is this init function. This is a function. You see that it starts with def. It is a function which is preceded by this underscore. There are two underscore and finished by two underscore. So the name is the conventional name using underscores. And all the functions, it could be many, that start and finish with names, start and finish with two underscore, are called dunder functions. I write here, dunder function. Dunder function. And they are also called the magic function. There are many. For instance, when you write plus, making the summation of two integer, 1 plus 2, this plus is a dunder function, which is not this one, head, and then some argument which are generally are the two numbers that you want to sum, two variables, A and B, for instance. A little bit more complicated than this one, but anyway, more or less is this one. So the class defining the integer number contains a dunder function, which is called add, that sums the two numbers. And A and B are nothing else, the instance of these two numbers, 1 and 2 here. And this is a sign, a symbol, which is the symbol plus. Simple this. So when you call plus, when you write plus, making the summation for integers, the interpreter will go in, well, first decide what these two elements are and decide that they are integer number and say, oh, these are integers, so they are members of the integer class. And then I look in the integer class for a function which is a dunder function whose name is add, double underscore add double underscore. And then he has the implementation, in this function, the implementation of the summation of the two numbers. Otherwise, if this, for instance, I want to write something like this, A plus B, this is a summation symbol. What the interpreter does is interpret the B and the A, and for instance, maybe that A and B are two lists. So the interpreter says, oh, I have two lists, so they belong to the class list, and the class list has a dunder function which is called add, which is translated by a symbol plus, that makes the concatenation of two lists. So the results of the calling to this dunder function will be not the summation of A and B in the usual way, will be the concatenation of the two lists. The same is true for other functions. The minus function is a dunder function which is present in the integer class, in the floating point class, and so on. These product function, these times, this asterisk here, the star here, will be make reference to a dunder function which is called prod, for instance, in every class. So every class in the Python kernel have different dunder functions that implement differently the meaning of the algorithm that are associated to the summation, to the product, to the subtraction, and to the ratio. For instance, also this one makes reference to a dunder function. So these are dunder functions. There are many dunder functions. I just in my example, in my course, I will only refer to the init dunder function. So any class can have. It also it is not necessary to define a dunder function like init here in any class, but anyway, it is useful. I always use an init. So when I create an instance of this class, you will see. Well, I'm not finished anyway. With the init. You see that I have this dunder function double underscore init double underscore. Then I have this parentheses and the name and the label here, which is called self. Conventionally, it is called self. It can be anything, but the variable, the name, which is the label, which is generally used to define classes, this self. Self will be substituted at the time of the, we will make an instance of the class, we will see shortly. This self label will be substituted by the name that we will choose for instantiating this class. So to be clear, now I run the cell, and you see here, I have fc equal constant class. This is an instance, I'm creating an instance of this constant class, and I will assign the name fc to this constant class, to this instance, not to the constant class, to this instance, and the self that you find here in the definition of the init function and in definition of all these variable here, which is called attribute of the class, will be, as the self will be substituted by fc. So now if I run this cell, everything is okay, I don't get an error. And now, if I want to retrieve the Avogadro number, you see that in the class I have self avo equal to a number, but in this self here is being substituted by fc. So I write fc avo, and I run the cell, and this is what happened. So I get it back the value of the Avogadro number. The same is true, of course, for the other variable that I have here. So init will define some convenient, depending on the class that you are building, convenient value for some called attributes. So everything which is defined this way in the init or in other functions of the class that we will define later is called an attribute. An attribute at the level of the class, at the level of the definition of the class, will be always defined this way: self dot a name of the variable, self dot a name of another variable, and so on. And in the instance, this self will be substituted by the name, by the label you choose for the instance of the class. I can also, this is not useful in this case, to define another instance of this class. For instance, I can write kk equal constant class this way. Not useful in this way, in this case, but anyway, just to see for demonstration purpose. And I can call, I can write here print FC started to get tired, so I write wish things. Anyway, print, no, kk, there you go. And you see the same value. So I have two instances of the class. And so I can call the attribute avo for the class, for the instance fc. I got the Avogadro number. Or also I can retrieve the value of the attribute avo for the class, for the instance kk. I got, of course, the same results, the same value back. Okay, so this is a class that probably is not useful to create many instances of the same class, but there are other occasions that you will have classes, and in your program you will define many instances of the same class, and everyone will get his attribute, method, and so on. Now, you delete this. Don't need it. Don't need it. Okay. Now I can use a function. I can write a function here that simply prints the attribute corresponding to the Avogadro number of this FC class. So I can write this func. I write the function, then I call it, and this FC avo is defined at the global level. So filter inside the function and can be printed simply. So when I call function, the messages will be printed as this one, the correct one. Now stop. Take into account that this is very useful because the function can very easily change the attribute of a class. So if I want to, if I have a variable elaborated in some way by a function, and I want to save this variable somewhere that can be accessed by other functions, assessed even at the global level, what I have to do is write in a class and put this value as an attribute of an instance of that class. And so I will have my value stored somewhere and can be used by other functions safely. And we will see tomorrow why it is safe. There's good practice work in this way. So just a very short introduction to class, and then tomorrow morning I will start again talking about this argument. Okay, question? Okay, if there are no questions, I will stop here, and we will start again tomorrow morning. Okay, goodbye.
Goodbye. Thank you.
Yeah.
Bye.